Good day, everyone. My name is Sachin Ravjee, and I am a bridge design engineer at Sutari, South Africa. I am here today to speak to you about the research which I conducted for my master's degree in structural engineering at the University of Pretoria, South Africa, entitled Discrete Element Modeling of Backfill Settlement Behind Integral Bridge Abutments. I will start off by giving a bit of a structural definition of integral bridges. I will then define the objective of the research. Next, I will briefly describe the discrete element method and give details about the software which I used, called BlazeDem. I will then describe the DEM modeling process and present the results of the study. I will end off with the conclusions and recommendations of the work. To describe an integral bridge, I will first define what a conventional bridge is. Let us consider a single-span bridge with a deck placed between two abutments. In conventional bridges, mechanical devices called expansion joints and bearings are utilized to accommodate the horizontal movements of the deck. This allows the deck to freely move transversely and longitudinally relative to its substructure. However, these joints and bearings require regular inspections and maintenance, as they have relatively short lifespans when compared to the structure itself. Integral bridges, on the other hand, are designed without these joints or bearings. This means that the bridge can be viewed as a single structural unit, as the deck and abutments are structurally connected. This means that the deck is restrained by the abutment for horizontal movement. When the deck moves because of thermal variation, braking loads, or creep and shrinkage, the deck forces the abutments to move with it. A particular concern comes from the cyclic loading due to daily and seasonal temperature variations. As the deck cools, the abutments move away from the backfill, and as temperatures rise, the abutments are forced back into the backfill. This back and forth movement of the abutments relative to its backfill causes a ratcheting effect in the soil. The objective of this research was to use the discrete element method to investigate the effect of particle shape on backfill settlement behind integral bridge abutments exposed to this thermal-induced cyclic loading. I will now give a brief description of how the discrete element method works. This method is a calculation cycle which solves for forces, displacements, and accelerations of individual particles. The method makes use of an equation of motion, a force contact law, and Newton's second law to do this. The discrete element method is an example of performing repeated, similar calculations about a time step delta t. A software package called BlazeDem was used to perform the analyses. BlazeDem is a research code developed at the University of Pretoria, South Africa, which is capable of offering elevated levels of performance when compared to commercial packages. The software can model spherical as well as polyhedra, both convex and non-convex particles. BlazeDem is based in the soft particle environment, meaning that particles are allowed to overlap one another to be able to replicate particle displacements. The way BlazeDem achieves its high performance levels is by performing the calculations using a computer's graphics processing unit, or GPU, as opposed to the traditional method of using the central processing unit, or CPU. A typical CPU consists of a number of high-speed threads, each capable of performing different complex tasks, such as running an operating system. A GPU, on the other hand, contains thousands of lower performance threads which can only perform the same much simpler task at a time. Consider the scenario where you need to transport thousands of passengers from London to Sydney. Using a CPU would be the equivalent of using a high-speed private jet. Each journey would be fairly quick, but you would need to make quite a few trips to get everyone across. In contrast, using the GPU is like getting a Boeing 747 for just a handful of trips. The trips may take longer, but because you can carry much more passengers, you would need significantly less time overall. As previously mentioned, the DEM calculation cycle is a large set of repeated calculations, all which are similar in computing terms, thus making the GPU ideal for performing DEM simulations. In previous research conducted, BlazeDEM was found to offer levels of performance up to 150 times faster than commercial codes which utilize the CPU. To perform the DEM simulations, a model abutment and deck was created. This included a 30-meter long deck with a 2-meter high abutment which could rotate about its base. A portion of the backfill adjacent to the abutment was modeled for the simulations. A 350 by 300 by 150 millimeter box was used. The box was filled with particles and the abutment wall was rotated 25 times towards and away from the backfill soil. To classify the particle shapes, a parameter called particle sphericity was used. Particle sphericity is how close a shape represents that of a perfect sphere. A perfect sphere has a sphericity of 1.0. As shapes get more angular, the sphericity decreases. The following particle shapes were used in the simulations: spheres with a sphericity of 1.0, dodecahedrons with a sphericity of around 0.9, cubes with a sphericity of 0.8, and tetrahedrons, the most angular of the particles, with a sphericity of just under 0.7. This video shows a sped up DEM simulation of the perfect spheres. Notice how the particles settle in a uniform manner compared to the red line. There is also relatively low settlement for these particles. Now, let us have a look at the more angular cubic particles. Again, pay attention to the settlement relative to the red line. Notice how the particles near the abutment wall settle much faster than those further away. Also, how much more settlement occurs compared to the spheres. The following settlement results were obtained when performing the simulations for the 4 different particle shapes. When assessing settlement across the DEM model after 25 cycles of the abutment wall, the spheres resulted in lower uniform settlements, whereas the cubes had higher differential settlement and higher settlement overall. The tetrahedrons, which are the most angular of the particles, experience the highest differential settlement. When the maximum settlement is plotted against the particle sphericity, a fairly linear trend can be observed. Particles with higher sphericities underwent lower overall settlement, whereas the more angular particles resulted in higher maximum settlements. A similar outcome is seen when comparing the differential settlement against particle sphericity. Again, the more spherical particles had less differential settlement, but the less spherical particles experienced much higher settlements near the abutment wall. The conclusions of the study can be summarized as follows. The magnitude of settlement and amount of differential settlement is related to the backfill's particle sphericity. When exposed to cyclic loading and unloading, particles with higher sphericities experience less settlement, which was more uniform. The more angular particles underwent higher differential settlement across the backfill. Lastly, based on the findings of this study, the recommendations to designers is: in order to limit the amount of differential settlement near bridge approaches, smoother, more uniform particles should be used as backfill. Recommendations for further research include considering different particle sizes and shapes with varying degrees of grading, modeling non-convex particle shapes, which have higher angularities than the particles modeled in this study, and performing full-scale testing. Thank you for your time, and I hope that you enjoyed my presentation. Goodbye.